Section 7.6 is on page 383, talks about transformation of discontinuous functions. We define what's known as the unit step function. The unit step function turns out to be if t is less than 0, 0, and 1 if t is greater than 0. It looks something like this. Of course, assuming this is t. So this is like when you switch a switch on, but the problem it stays on forever. By shifting the argument of u of t, the jump can be moved in a different location. If I look at how this looks, if t is less than a, then this is 0. We're going to assume always we're talking about positive numbers, so this really doesn't come into play for us. And once we hit a, you switch it on. To shut it down, you need to really make a negative after one of those. And we'll talk about that when we get there. This is called Heaviside function. It's very famous. So I'll show you what this works. This one comes really from the one in front of us. If you put an m right there, when you switch the system on, when you hit t equal a, it's really 1 times m, and that's what you end up with. Now, the Laplace of this unit function, that's what this is, unit step function, is e to the negative a. Notice this is the same. There's a 1 in front of u. So the shift is taken care of by this. And what's in front of u, remember the Laplace of 1 is 1 over s. And that's how it works. So you always look in front of it to figure out what's there. And those I will get around really quickly as I do examples. You could shift a function by e to the negative a, and the function itself is f. And similarly, if you could go this way, you could come in reverse and do it this way. So let me show you how this works really quick. I'm going to start with some examples. I'm looking at example number 1. It says, sketch the graph. So at 1, there's a 1 in front of this. You turn the system on at 1. So it's 0 before that. Now, we normally stop right there. But you could run it down if you want. Doesn't matter. But when you hit 1, this system turns out and becomes a 1. And it runs infinite. But this system at 4, it turns on. And since it turns on and there's a negative 1 in front of it, what it does, it takes this and it subtracts 1 from it. So this system runs only between 1 and 4 seconds. In 1 second you turn the switch on, and in 4 seconds you turn the switch off. Now, it's a sketch the graph and find the Laplace. If you apply the Laplace on this, if I look at my formula sheet, Laplace associated with t is number 11, e to the negative as times f, or number 10. If we're not dealing with a function yet, it's simply 1 or 0. It is e to the negative as, where this is a, divided by s. And I'll show you where that comes from so we grasp this. So there's a 1 in front of this. The 1 gives you 1 over s. And this gives you e to the negative s. Minus, there's a 1 in front of this. And when you apply the Laplace on that, that's 1 over s. And this is taken care of by e to the negative 4s. So that's the Laplace transform of this. if I look at this graph, it should be y equal t. Y equal t is a simple, straightforward graph that cuts the quadrant exactly in half, assuming this is the t-axis, y equal t. But this doesn't turn on until 1 second. So from 1 second and on, this turns on. Before that, you're at 0. Again, we normally run to the origin. We say this is the graph, but you could run it all the way down if you wish. Now, if I want to apply the Laplace transform on this, I look at the formula sheet and I notice it must be that the function has the same unit. So those must match. You can't control the unit, you could control the function, meaning I could say this is really t minus 1 plus 1 u of t minus 1. So this times that, that's u minus 1, oops, that's t minus 1 u of t minus 1 plus 1 times u of t minus 1. And since a number cannot be shifted, that always matches the shift. Now if I apply the Laplace transform of this, the shift is taken care of, this shift is taken care of by e to the negative s. That makes this simply a t. And you're applying the Laplace on t, which is 1 over s squared. Here, the shift is being taken care of by e to the negative s. There's a plus. And the Laplace of 1 is 1 over s. And this has tons of applications, which is why they're given it its own place in this. Express the given function using window and step function and compute its Laplace transform. Alright, we're not going to worry about the graphs of those, but let's see how this works. Between 0 and 2, this is 0. Okay, so g of t is 0 plus, no need to write that, when the system turns to 2, you really get t plus 1. There it is. You could say this is u of t if you want, but that's 0. So again, I need this to match that. There's no control over this, but I can control this by saying, well, g of t is t plus 1. I want it to be minus 2 plus 2. So I'm doing this because students normally have a hard time seeing if I skip and just write what's next. So I want t minus 2 plus 3. I would skip this step, but again, students have a hard time jumping from this to this. And the reason I do that, because now I could say g of t is actually this times this plus 3 u of t minus 2. And the reason, if you shift 3 left or right, it remains the same. So this already includes the shift. Any constant function, you could shift left or right and it doesn't change. If I apply the Laplace transform on this, I will get the shift is taken care of by e to the negative 2s. That leaves me with t. And the Laplace of t is 1 over s squared. Plus the shift is taken care of by e to the negative 2s. And the Laplace of 3 is really 1 over s. Now I do want to mark this. This is using number, I forgot about that part. This is using number 11. Every time you use that, and 1 and 2. 11 and 1 and 2. Right? Alright. Now we get to number 8. I want to figure out a formula for this. And how does this work? Well, let's see. I notice here we have g of t equal 0 times u of t, all the way until you reach pi over 2. Plus, when you reach pi over 2, the system turns on. So what do they want us to do here? The same deal. They want us to actually take g of t, and isn't this the sine of t minus pi over 2 plus pi over 2? Now I could have used identities, but I don't want to throw you off. And isn't this sine of the first cosine of the second plus sine of the second cosine of the first, cosine of a plus b? And isn't this that a 0? So that's gone. Isn't that a 1? So now, since they match, if I apply the Laplace transform on this, I'll get f of s to b, and to take care of the shift, that is e to the negative pi over 2s. That leaves me with cosine of t, and the cosine of t, if I really apply the Laplace, that's s over s squared plus 1. So we said that's by 11, and this is by, I believe, 8. No, this is by 6. And if I look at number 10, the g of t equals 0 times u of t, t minus 0 really, and this system turns out when you hit 1, and it becomes t minus 1 squared. Here it matches. So g of t equals t minus 1 squared u of t minus 1. So when I apply the Laplace transform on this, I'll get capital G of s, or f of s, whatever you want to call it, to take care of the shift. That's simply e to the negative s. That makes this simply a t squared, and the Laplace on t squared is 2 factorial divided by s cubed, and I believe that is 3. That is 3. And of course, 11. And now if I just want to find what those are really quick. This is just a quick practice. If I want to go backwards, it says determine the inverse Laplace transform. I want to go from right to left, so I'm looking at this table, and I'm looking, there's only one e, it's right, actually 2 of them. This is for the unit step function, but this is for any function. So you go from right to left, you have to take care of the shift, and then whatever f of s, you go for f of t, just like we did prior to this. So let's see how this works. If I apply the inverse Laplace transform on this, e to the negative 3s will take u to the 2 minus 3. 1 over s squared, if I look at where does 1 over s squared come from, that's really right there, number 2. It should be t. By 2, it should be t, but I have to shift it by 3 because of that shift. So instead of t, it's going to be t minus 3. And that's how it works. Fairly simple. Here, the same deal. If I want to apply the inverse Laplace transform on this, well, I'm looking at really u of t minus 3. So it's going to shift everything by 3. Well, 1 over s squared plus 9, I have to multiply by 3 and divide by 3. 3 over s plus 9 is a sine of 3t, so it's 1/3. It should be the sine of 3t, but it's shifted. Instead of 3t, it's going to be the sine of 3 into t minus 3. And this is by 11 and by, I believe it's 5. It is 5. Don't mix this e with the e we're doing right now. That e is only for the unit step function. Alright, and how about this problem? If I apply the inverse, I should multiply by 2 and divide by 2 because this is a sine again. It's 1/2. It should be the sine of 2t, but instead of 2t, since I have a shift of t minus 1, I should make that minus 1. That's probably the easiest way around this. And when I get to partial fraction decomposition, I need to split this up, and this turns out to be e to the negative s times. And if I work this out, that will work out to be a over s minus 1 plus bs plus c over s squared plus 1. And that's what it turns out to be. Now, I am aware that this is negative 2e to the t, and this is cosine of t. I know that. But when I apply the inverse Laplace transform on this, that's going to be negative 2e. It's going to be shifted by t minus 1 because of that, plus this should be a cosine, but it's going to be shifted by a t minus 1, and both of those are going to be multiplied by u of t minus 1 for the system to turn on. You could do those individually, you could do them combined at the same time, that doesn't matter.